Okay, so now the lecture is officially being recorded, and I would like to start with a recap of yesterday's discussion. Um, so we have discussed that according to Maxwell, light is an electromagnetic wave, and the theory that Maxwell discovered was in very good agreement with experiments. And I mean, the fact that he could describe light as being an electromagnetic wave was, let's say, the final word about what is the nature of light. And then I started discussing with you the profile of the radiation emitted by a black body. And you see that I started this section with the name of Planck, Max Planck. So Max Planck is the first character that appears in our discussion about the roots of quantum mechanics or quantum theory. So before I talk about the contribution that Planck gave, let me remind you what we discussed. So I told you that as soon as you hit a material, namely if you give heat to the material, then this material will emit radiation that we call as thermal radiation, okay? And of course, if you now send radiation towards the body, this body will also absorb radiation. So a heated body can emit and absorb radiation. But there is a special class of materials that we call black body that absorbs all the radiation that is sent towards it and does not reflect any radiation. So if you send radiation towards this body, it will absorb everything, but it still emits thermal radiation because it's heated. So if it has a high temperature, it will emit radiation. And of course, I mean, even with low temperature, but if you increase the temperature, then the radiation can start becoming visible. And so the concept, the very definition of a black body is a material that its surface absorbs all the radiation that hits it. So they don't reflect light. And at a given temperature, all black body, I mean, irrespective of the material that you have, if it is a black body, then the radiation profile that it will emit is the same. So if you have a black body A and someone else has a black body B, although they can be different things, the thermal radiation emitted by a black body is universal. And by universal, I mean that if those bodies are at the same temperature, then the radiation profile will be the same, okay? Now, we move to the second part of this slide, where you see this plot. And this plot is the intensity of the emitted radiation against the frequency of the radiation. So as I said, the frequency tells you how many oscillations per second this radiation will perform. And the intensity, if you want to give a description of what is it in simple words, is the amount of light that you have. So if you have more light, then you have more intensity. But this is a very simplistic way of explaining what intensity is. This plot represents the outcome of experiments. So what I'm saying is that at a given temperature T1, so I have a body, and this body is in thermal equilibrium. So all the body has now the same temperature, and I'm calling this T1, okay? And I'm saying that if now you measure the intensity of the radiation emitted against the frequency, you're going to see a curve as this green curve that for very low frequencies, it starts going up until some maximum value of intensity, and then it starts going down after this maximum until for very, very large values of frequency, the intensity goes to 0, okay? Now you can ask what happens. This is important to remember. Every black body at given temperature T1 will have the same curve, okay? Now, if I give more heat to this black body and I heat this black body until temperature T2, which is bigger than T1, and now I ask, what is the radiation, the intensity profile? Then I will see a curve, this blue curve, that is very similar to the green curve in shape. But as you can see, the peak of this curve is higher than the green curve. So if you this letter that I use to represent the frequency is a Greek letter called nu. So nu1 is smaller than nu2, and it is precisely at nu2 that the intensity of the radiation emitted by the black body is maximum. So if I increase the temperature from T1 from T2, I also increase the value of the frequency where the maximum is achieved, okay? Now, if I increase even more the temperature, if I move to T3, then you see that the peak is also higher. So the intensity, the maximum intensity goes to a higher value. So it's around here. And you see that also the frequency at which the intensity is maximum increased. So as soon as I start increasing the temperature, I'm also increasing the frequency where the intensity is a maximum. This is what you see from experiments, okay? So this is not a prediction from a theory. This is something that you measure in a lab, okay? So there are a couple of questions. The first one is, just a second. Okay. Are we considering time in this graph? No, we are considering the intensity against the frequency, okay? The frequency counts how many oscillations the wave perform at a given unit of time. But this is the frequency, not time, okay? And then there is a second question, which is, this intensity we are measuring is just for black bodies or it works for other materials? No, so the intensity is a concept about the wave, about radiation. So you can measure the intensity of an electromagnetic wave irrespective of the material that emitted this radiation, okay? What I'm saying and what is special about black bodies is that the intensity has this profile that I described here. So this curve that goes up and go down, irrespective of the material of the black body. But of course, I mean, if you pick up a completely different, like a piece of metal that you just heat it up, it will emit some radiation, and you can measure the intensity. Does that clarify the questions?
Hello. Please, the diagram we have here, is it representing for the V ones? Is it that with the black bodies they only emit the maximum frequency, or there are other frequencies that could have been lower than the respective mu i's, as in running from 1 to 3?
So what you see from the radiation emitted by the black body is all this collection of frequencies. But there is one frequency for each temperature that you have maximum intensity. Okay? So it's not that the body will emit just waves with this intensity. It is just that the radiation emitted at this frequency has the maximal intensity. Okay. There is another question. Is there?
Hello.
Hello.
Yes, we are saying this graph is for every black body. Are we
This is,
considering this graph? I'm talking about one at certain temperature T2 T1.
yeah,
Okay, whatever the material this black body made of or the shape of this black body, it will give me the same shape.
yeah, that's correct.
Oh my God.
Okay. Then there is a question by Silas. Is the intensity related to the amplitude of the wave? Yes. So the intensity, if you know the theory of electromagnetic waves, the intensity is related to the amplitude of the wave, which in turn is related to the amplitude of the electric field. But for our purposes, you can think, I mean, if you think of a wave, right? If you think of a wave that goes up and down, the amplitude is essentially the height of the wave. So yes, you are correct. This is related to the amplitude of the wave. Yes. Can I move to the next slide, or are there more questions? Do not hesitate to ask. So. Okay, so I will go ahead, and if you think about some question that you'd like to ask about this thing, just let me know. Okay, so I'm not so sure why I cannot move my slide. Or maybe I have to move with the pen. Yes. Okay. So you see that as we said, for different temperatures, there is a question. Yes, T1, T2, and T3 are different temperatures, but different temperatures of the same body. So in the first situation at T1, the body is at thermal equilibrium and the temperature is T1. Then as I hit the body, it goes to temperature T2, I make the measurement, and then I hit it again, and it is going to be in thermal equilibrium at temperature T3. So it's the same body. Okay, good. So as we saw, for different temperatures, the qualitative behavior of the intensity as a function of the frequency is the same, right? So there is this thing of going up and going down. So I see that there is a question. I will reply that in a second. So starting from very low frequencies and move towards larger values, the intensity grows up to a maximum and then it goes down. Okay. As we also discussed, the larger the temperature is, the bigger the frequency where the intensity is maximum is. So as you increase the temperature, the frequency where the maximum of the curve occurs goes to the right, goes to larger values of the frequency. Okay. So let me see the question that we have in the chat. The curves are the radiations. Yes. So the curves are the intensity of the emitted radiations by a black body at different temperatures. Okay. So yesterday we were talking about how to construct a black body, actually. So there is a practical way of constructing a black body, which is the following. If you take an object and the object has a cavity inside it, so think about a ball, and then inside the ball, you take the core of the ball, so you make a cavity, okay? And this cavity, it can be connected to the external world by a very, very tiny hole. So you see that here I have the ball that I talked, I removed the core of this ball and I made this tiny hole. Okay, this is a cavity. Okay. So now I can see the following. A black body is such that if I send radiation to this body, then it should be absorbed. Of course, I mean, if this is just a random material, I send radiation, part will be reflected and part will be absorbed. But now look just at the small hole that I made here, and I send some radiation in, okay? You see that the radiation enters the cavity, it will hit the wall of the cavity, it is reflected, it hits again the wall of the cavity, it is reflected, once again, and then at some point, this radiation that entered the cavity will be absorbed. Okay? It's very unlikely that the radiation that enters here after hitting these walls several times will go out. Of course, you can have some radiation that will escape, but the amount of radiation that escapes, it's much less than the amount of radiation that is absorbed. So if you look from the perspective of this hole, namely, if you're just making measurements around this hole here, then this body behaves as a black body because all the radiation that you send to this body is absorbed. Okay? So this is a very practical way of constructing a black body. But as I said, you have to make measurements around this hole here. No transmitted I didn't get Mahmoud. Is this a question or?
Hello. Here we are considering just only the reflection of ray, reflection and absorption.
Yes.
Nothing transmit outside from this cavity.
Yeah. So of course, in the real world, some radiation can escape, but I can make this hole very, very tiny in such a way that, I mean, the chances of something escaping is very, very low. Okay.
Okay. That means the only chance to this ray to get out of this cavity from this small hole.
Yeah. So typically, what will happen with the radiation that enters the cavity is that it will be absorbed by the walls of the surface of the cavity. Okay.
Okay. Thank you.
You are welcome. There is a question: why there is no possibility for the radiation to get out from the same hole? There is this possibility, but as I said, so if you think about the very complicated path that these rays will go inside the cavity, the chances that it goes out, it's very low. So it can go out, but most of the rays that enter this cavity will stay inside. Okay. Will such a body have absorption limit? Well, of course, if you are, the point is that the wall absorb radiation, but also the atoms that made this wall will also emit radiation. Okay, so it's it does not only absorb, it also emits. Okay. Is the composition of the material essential in this construction? No, I mean, what I'm saying, of course, when you go to a lab and make real things, there are some materials that are preferred instead of the others. But for us here, the material does not matter much. It's just that you have a cavity and this very, very tiny hole. Okay? Okay, let me move. Okay. Please, is the emitted radiation different from a photon in this case? So we didn't introduce the concept of photon yet, but you're going to have a answer to this question soon, I hope. Okay. Okay, so there is a question which is, but is it not possible that a small proportion of radiation is emitted? Yes. I cannot understand, is it absolute or we suppose this negligible? No, it is It's not only possible, but it's going to happen. But the amount of radiation that is emitted is very low compared to the amount of radiation that is absorbed. So it's negligible. Okay. Okay, so now I will move on, and if you have further questions, I will answer later. Okay. Okay. So as I said, this is a practical way of constructing a black body, and this is summarized here. So if the hole is sufficiently small, just a negligible amount of incident radiation will be reflected and escape from the cavity. So what is important here is that most of the radiation that enters will remain inside. Just a very tiny fraction will go out. So that's why we can call this a black body, in the sense of absorbing all the radiation that enters the body from this small hole. Okay. So if you measure the radiation that will be emitted here, okay. So do not make confusion. So the body absorbs this radiation that comes from the outside, but inside the body, of course, the body will emit radiation, because as we discussed, all bodies at some temperature will emit thermal radiation. So I can measure the radiation that this body will emit. And this radiation that is emitted by this body will be similar to a black body profile. Okay, so now that I introduced to you the concept of a black body, we can ask, what does the classical theory of electromagnetic waves predict for the intensity as a function of the frequency? So I have shown to you that this is the outcome of the experiment. So this is what you measure. So if your theory is good enough, then you should reproduce something like that. Okay. But now let us see what the theory gives to us. So I will not do this calculation, not because it's not interesting, but because we don't have time. And also it requires some knowledge that I'm not sure if all of you have. And since this will not be important for the rest of the lectures, I don't want to explain to you all these things that we will not use later on. Okay. If you want to discuss more about that, we can, but during some extra time. I'm happy to do so. So now, if I want to compute the intensity against the frequency for a black body using the classical theory of electromagnetic waves, what you see instead of a curve like the green one that was measured in the lab is a curve like this dashed blue one. So given a black body, if I just use the theory of classical radiation and compute what is the intensity against the frequency, I'll get this curve. So you see that the classical theory predicts that the intensity will just grow with the frequency. And you see that for very low frequencies, this classical prediction is very, very close to the outcome of the experiment. So for tiny, tiny frequencies, they agree. However, when I go to very high frequencies, or when I get close to the peak, to nu 1, you see that the classical prediction is completely different. And in particular, if I go to very high frequencies, the results of the experiments tell me that the intensity must go to 0. And in the classical prediction, this intensity just go to infinity. So these are totally different predictions. Sorry, these are totally different results. the classical prediction and the experimental outcome. So there is another problem, is that if you do the calculation carefully, you see that the intensity as a function of the frequency using the classical theory is something proportional to the frequency to the cube. And if you want to compute the energy that this emitted radiation has, you have to integrate, namely, you have to compute the area below this curve. And if you consider this curve here that blows up and goes like nu to the cube, if I integrate the area below this curve, this will give infinity. So this will be infinite. And therefore, this is a very unphysical property, right? I'm just saying that the energy carried by the radiation emitted by a black body is just infinity. Okay? So, it's just infinite. So it's a completely non-physical prediction. While for the result coming from the experiments, if I integrate, namely if I compute the area below this curve, I'll get something that is finite. Okay? You see that this problem occurs, so the classical prediction becomes worse and worse as we go towards higher and higher frequencies. And radiation with high frequencies are called ultraviolet, because the problem gets really bad when we go to high frequencies, and when we go to the ultraviolet region. This was called at the time as the ultraviolet catastrophe. So the fact that you go up, 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 and this is unbounded and just go up to infinity for very high frequencies, then you get this unphysical prediction, which is the energy being infinite. And this was called as the ultraviolet catastrophe. And actually, the classical expression that gives you the precise relation between the intensity and the frequency is due to Rayleigh and Jeans, and this is also called the Rayleigh-Jeans catastrophe. Okay? So if you just use classical theory of radiation to predict the behavior of the intensity against the frequency, you get a result that is completely non-physical, and you start asking yourself, how do we fix that? So I have a classical theory that I trust, which is Maxwell's theory. I know how to compute the intensity of radiation using such a theory, and I compute it. I go to a lab, I make a measurement, and these curves are totally different. Okay? So you can think, well, maybe Maxwell's theory is wrong, but of course the theory was tested in very different systems, and it always gave very good results. So you can start thinking, what is the problem? I mean, why do I get a completely different result from my theoretical prediction and the experiments? Okay. And now enters Max Planck. So Max Planck in 1900, Max Planck wanted to explain how this blue curve was wrong and why this green curve was correct from the theoretical perspective, because this was correct, because this was what was measured. So you cannot dispute facts with nature, but of course, Max Planck, as the other physicists, wanted to explain why this is the case. And for that, Max Planck made a very non-trivial and non-intuitive assumption. So we know that when the body absorbs radiation, the radiation carries some energy, okay? And therefore, the radiation, when absorbed by the body, will give energy to the system. And when the system emits radiation, the system will giving away energy, okay? From a classical theory perspective, this can be done by whatever value of energy is transported by the radiation. So if you have some radiation that carries some energy, then the body, namely, for instance, the black body, can absorb every amount of energy that you give to it. So it can be a tiny fraction, it can be a larger value, but it is a continuum possibility. So the system can absorb whatever is the value of the energy. And what Max Planck said was, this is not true. Actually, the system can just absorb or emit energy in specific values. So see, this is very different from what the classical theory tells you. The classical theory says that the system can exchange energy, whatever value the energy is. And now Max Planck is saying, well, actually, energy must be exchanged in certain amounts, certain specific amounts, okay? So think about, you have a collection of balls and you want to, throw these balls against a wall, okay? You know that the amount of energy that you can hit the wall depends on the fact that a particular ball is hitting the wall, okay? So you don't have a continuum flux of energy, but rather you have bodies, small bodies, hitting the wall one by one. And these bodies will transport certain amounts of energy. And what Planck was proposing is that the radiation will exchange energy with the material just in packets of energy. So the radiation gives some packet of energy to the system, and the system gives some packet of energy out. This is highly non-trivial. And this packet that you give of energy, that radiation gives to the system, is called a quantum of energy, okay? So now you're saying that the system does not exchange any amount of energy, but just quantum of energy. And the plural of the word quantum is quanta. So the system will exchange energy just in quanta of energy, okay? And so just to let you know that I see that there are some questions in the chat. I will take them soonish, okay? So you see that the sentence summarizes what I said. Instead of having a continuous energy exchange between radiation and the atoms, the cavity's wall, Planck postulated, so he didn't have a more fundamental explanation for that. He just said that this was the case. Postulated that the energy is quantized. So I don't even understand my own letter. So, so if you have some frequency nu, an atom of frequency nu can just emit or absorb energy as integer multiples of an energy quantum or a quantum of energy. Okay, so going to the next slide. This is this is the quantum that I'm referring to. So now the radiation and the atoms that compose the surface, the walls of the cavity, they can just exchange energy as multiples of this number, which I have this constant h and the frequency nu. And this can also be written as h bar. So I have this different name. And omega. Omega is the angular frequency. I'm going to explain to you what is that. So Planck said that the energy should be a multiple of 8 nu, and h is what is called as the Planck constant, and this is a new fundamental constant of physics. So the Planck constant has this value, 4.136 times 10 to the minus 15 electron volts times second. And this is also approximated by this value if you want to write this in joules. So joules times second. Joules is the dimension that you use to measure energy. And h bar is just the Planck constant divided by 2 pi. Okay, so if you take this number and divide by 2 pi, this is what we call h bar. We are going to encounter h bar all over the place in these lectures. So you are going to get used to that. So just to summarize, Planck told us that radiation exchanges energy with the material as multiples of this h nu, where nu is the frequency and h is the Planck's constant. So energy is not a continuum variable that can take whatever value you want, but is a discrete variable. It goes as packets of energy. So you can have either one quantum of energy or two quanta of energy, but you cannot have a square root of 2 times h nu amount of energy. Okay? This is very important, and this is at the heart of quantum mechanics. Okay. So let me just go on a little bit more, and then I'll take the questions. So this is an equation that some of you probably saw, but the point is the velocity or the speed that a wave propagates is related to its frequency. Okay, so if you want to talk about visible radiation, then the wavelength, if you think about a wave, it is the distance between two peaks of this wave. So, and we denote the wavelength as lambda. This is a Greek letter called lambda. Okay. For a visible radiation with wavelength lambda equals to 5,000, and this letter is angstrom. So this is just a name for 10 to the minus 10 meters. So if you have radiation with wavelength lambda, then we can use this very well-known equation that relates the speed of the wave propagation. So this is the speed of the wave. This is equal to lambda, the wavelength, times the frequency. So if you know the speed of propagation of some wave, and if you know the wavelength, you can discover the frequency. So here, I told you what is the value of the wavelength. And I'm talking about radiation. Radiation moves with the speed of light, and we know that. This is 3 times 10 to the 8 meters per second. We saw that yesterday. So if I want to discover what is the frequency of this radiation, I come just to this equation, replace the speed v by c, and write that the frequency is c divided by lambda, where lambda is the wavelength. And this will give to you that the frequency of this radiation, the visible radiation, is 6 times 10 to the 14 seconds to the minus 1. This unit, seconds to the minus 1, is also called hertz. Okay? Now I can ask you, for this radiation with this particular wavelength, what is the value of the energy, what is the value of the quantum of energy transported by this radiation? So I just come to Planck's formula. Energy is Planck's constant times nu. I just discovered who nu is 6 to the times 10 to the 14. And I just multiply this number by Planck's constant, which is given here. So I can use, since I'm using here, I can use the units of joules. So the energy is 3.98 times 10 to the minus 19 joules. If you are familiar with energy, with the concept of energy, this is a very, very tiny energy, value of energy for our typical macroscopic world. So the quanta of energy transported by radiation is very, very small, it's tiny. However, I can convert this energy that was expressed in joules to electron volts. This is another unity to measure energy. So 1 electron volt is approximately 1.602 times 10 to the minus 19 joules, and the energy is then 2.5 electron volts. And if you go at the atomic scale, now if we're looking at systems that are very, very small, this is not a tiny amount of energy. Actually, this is a considerable amount of energy at the atomic scale. So you see that the quantum of energy that is transported by the radiation for our macroscopic world is very, very tiny. But if you go to microscopic scales, the amount of energy transported by the quantum of energy is not negligible. Actually, it is comparable to typical energies of the system. So you cannot neglect the fact that energy is transported by quanta of energy. Okay. I will just talk about this first part of this slide, and then I'll take the questions. So, if you learned a bit about thermodynamics, if you didn't, no problem, because this is just to make a comparison that you're going to understand. You know that thermal energy is encoded in this product, the product of the Boltzmann constant, Kb, and the temperature of the system. This constant Kb has this value that I wrote here. So it's 1.381 times 10 to the minus 23 joules per Kelvin. And if you go to very high temperatures as 10 to the 4th Kelvin, the thermal energy, kBt, is of the order of 1 electron volt. And if you compute how much is the thermal energy at room temperature, so if you measure the typical room temperature, you're going to find something of the order 1 divided by 40 electron volts. So quantum effects will become really important when the product of the quantum, when the value of the quantum energy is bigger than kBt, which is the typical thermal energy. And if you saw some statistical mechanics, if you didn't, no problem, it's just to make the argument. You know that you can find a particle, a state with energy E with the probability given by this so-called Boltzmann factor, which is exponential of minus E under kBt. So if E is much bigger than kBt, then this goes to 0. And this is exactly the suppression that we saw in the previous plots. So if you come back, you see that when the frequency grows, the chance of getting a state with high frequency goes to 0. And this is exactly what we're seeing. So by saying that energy is transported by packets of energy, and that you could, look at the probability of finding states with such a given energy using statistical mechanics, Planck has explained why the curve had this behavior of going up and then going down. So you see that you use this statistical mechanics bit, and you can explain the curve. However, the fact that Planck postulated that energy is quantized was totally not justified a priori. So Planck didn't have a fundamental explanation why energy was quantized. In fact, there are some books that say that Planck simply confessed at some point that this was total desperation. I mean, he wanted to find an explanation for the curve, and then he tried everything. In particular, he tried this discretization of energy. And if you try to explain Planck's argument using classical physics, you fail. So Planck actually postulated something new, and this something new will be explained under the framework of quantum mechanics. But this is the very first evidence of a departure of classical physics. We have to add something new to the game. And this is one of the very first signals that classical physics was not complete, was not a complete description of nature. Also, the energy of the oscillation depends on its amplitude and not on the frequency. So the intensity, as we discussed before, I mean, is associated with the energy, and the energy for the classical theory can just vary continuously, while in Planck's theory, you cannot. This cannot vary continuously, just as discrete amounts of h nu, okay? And this is the very first signal that treating radiation as a wave can bring some problems. Because if you assume that electromagnetic radiation is just a wave, as Maxwell predicted, then you cannot explain the radiation emitted by a black body, okay? So this is the very first signal that our understanding of light is not complete. And we are going to have a break now, but I will discuss another phenomenon that will require some departure from classical physics. But before the break, let me take a look at the questions. So the classical prediction goes to infinity always. The answer is yes. So there is a question before that, sorry. When you check the process inside the black body, is it clear there is a formation of total internal reflection? What happens if the light ray fall exactly at the hole of interest? Well, if the ray just hit the hole, it will go out. And this is not a problem. I'm just saying that the amount of radiation that will escape is much, much smaller than the amount of radiation that will be absorbed. Someone said, you mean discrete amount of energy? Yes, I probably took long to say the word discrete, but yes, when I say that energy is transported as, packets of energy, I mean discrete amounts of energy, yes. So Abdallah said, yes, that's correct. Then there is Felix wrote anathom, but I don't see. So I don't understand, Felix, what you meant by that. The wavelength we are considering is the wavelength of the radiation. Yes. Can you please explain this part? The energy of the oscillation depends on its amplitude and not its frequency. Yeah. So this is a classical result. So if I ask you, what is the energy of transported by some electromagnetic wave, then the classical theory says that it depends on the amplitude of this wave, but it does not depend on the frequency. And what I'm saying here by looking at this equation is that the energy actually depends on the frequency. Okay? So that's the difference. So this is not a classical formula. Okay? So can you please go back to page 7? So here is page 7. Is there a specific question, or you just want to have a look at page 7? Okay. So we started by saying that light was a wave, and we are concluding that the energy is released in discrete amounts. Following your analogy of a ball thrown against a wall, one that means light is then behaving like a particle moving at discrete times. Is light then both a wave and a particle? Well, just to be careful with these discrete times, I'm not saying anything about discretization of time. I'm saying things about discretization of energy. But apart from that, what you said is right. I mean, if you want to follow the analogy that these packets of energy are arriving one by one, then you can think as light as a collection of tiny, particles that transport this quanta of energy. Then you said, is light then both a wave and a particle? The answer is yes, but we are going to discuss that. So this is a spoiler, so I'm telling you yes. But as we are going to see, this is not a particular property of light, okay? And we are going to come to this point. Okay, so Paul, you were copying something from page 7. Let me also say that I will post these slides, so you don't have to really copy things. But I know that some people prefer to copy, otherwise they get bored and so on. But I'm just saying that if you miss some details, don't worry, okay? Okay, so I think I answered all the questions in the chat. If not, please let me know. And now we go for a 10 minutes break, okay? So it's 12 now, and we come back 10 past 12, okay? So I will stop the recording, and when we come back, I will record again, okay?